Welcome to another one of our Siemens SolidEdge portfolio webinars. This one is titled 10 Techniques for Easier Product Design from Start to Finish, and it's part of a series of digital transformation webinars focused on speeding your product development and manufacturing process and helping you deliver world-class products to your customers. My name is Ilya Nezurenko, and I'm your host and presenter for this webinar. In the interest of time, we will not have a separate Q&A session at the end of this webinar, but you can key in your questions to the SolidEdge community forum shown at the end of this webinar, and we will get back to you to answer your specific questions. The SolidEdge portfolio is focused on driving digital transformation for small and medium-sized companies. We see that these companies want complete, fully featured and professional engineering tools, but they also need tools that are easy to access and easy to learn. As you'll see in this webinar series, the SolidEdge portfolio is more than just SolidEdge CAD. It's a complete portfolio of solutions for design, simulation, manufacturing, and technical publications. Also, we have tools for collaboration and data management. Combined, these solutions speed the complete product development process. With the SolidEdge portfolio, you can create detailed 3D digital models, also known as a digital twin, of your proposed products and use these as the basis for all areas of product development, including concept and detailed design, prototyping, simulation, manufacturing, installation, and service. This digital twin also helps small to medium-sized businesses address major challenges like increased complexity and increasing regulations. Before we dive into SolidEdge, I would like to share with you some relevant for today's topic information. A notable industry consultant, Aberdeen Group, took a survey of design and manufacturing companies and found some interesting statistics that tied the top technical limitations to business challenges. Aberdeen's study found that 39% of designers struggle with model creation when using a traditional 3D CAD tool. If you've ever used a traditional 3D design tool, you're probably aware of some of the technical challenges that stand in your way. These systems require models to be built in a certain way and use complex rules to preserve shape and size. Aberdeen also found that 57% of designers and engineers lack the ability to alter existing designs. Traditional CAD requires models to be built and edited in a certain way, making fast, flexible changes difficult. In fact, over half the respondents claim that traditional history-based systems require the original designer to make the change because of the complexity. Lastly, is your company looking for ways to reduce overall product or product development costs? Are you looking to better reuse existing data from previous designs? How about reuse data provided by external suppliers or customers? If you said yes to any of these questions, you're not alone. 44% of history-based 3D users worry about having the ability to deal with this as well. Most 3D CAD systems can import data, but making edits or integrating parts into existing designs is problematic. Oftentimes, remodeling is the only option, which means wasted time and money in a non-value-added activity. Do you want to improve your design process but not sure where to start? Industry research shows that an investment in better design tools or methods will have a profound effect on companies' bottom line. Today we're going to focus on design capabilities of SolidEdge. SolidEdge makes creation and editing 3D CAD models faster and easier through our unique synchronous technology. The most common type of CAD system available in the marketplace uses what's called history-based modeling because it has great benefits such as being dimension-driven. It's so good, in fact, that SolidEdge has been a history-based modeler for more than 20 years now and continues to provide this method. However, we worked this way for so long that we've learned to ignore the not-so-good things, such as having to pre-plan the model. Looking at a better way to work, we can turn to direct modeling because this has some great benefits, such as direct interaction with the model. But there are downsides to this method too, such as being featureless, so not very organized. How about taking the best of the both worlds, but leaving out the downsides? This is why Siemens created synchronous technology, combining feature-based modeling and dimension-driven designs with flexible editing using direct model interaction. But it didn't stop there. Synchronous technology delivers additional functionality such as procedural features, face relationships, and 3D driving dimensions. Let's take a look at Solid Edge in action. We're going to be working on a real motorcycle model, which was actually designed with Solid Edge. The goal here is to add a new foot lever while ensuring its fit and function. In the process, we will virtually test our design using built-in Solid Edge simulation capabilities and edit as required to make sure it has sufficient strength. Let's switch to Solid Edge. Here's a motorcycle we're going to be working on, and as I mentioned earlier, we're going to be focusing on this area where we need to design the foot support or lever for the left foot. Quite easily in Solid Edge we can switch to a desired set of components using display configuration, and we're ready to start creating our lever. In one single operation we're going to define position, location, name, and material for this new component. We're going to start our design by grabbing the face of an adjacent component and producing our first 3D geometry. This is a great way to accelerate your design right from the start. Now I'm going to add some additional geometry, and I'm going to start by projecting the edge of existing cylinder to a plane. It's quite easy to do, and one thing you'll notice that I'm not going into sketches, I'm not going to any features, I just simply grab the edge and project. The same way I'm going to define the rectangular shape. You can see system gives me virtual intersection, and this is where I can define my rectangular shape and continue with my design. Solid Edge is very flexible. I can select the sketch and reposition it to any new location. I want to do that because I need some step, but in general you can take the sketch and reposition to any location and redefine this 3D geometry again using the sketch. In this case I'm not going to do that. I will simply continue my design by copying existing geometry, and that would be another great productivity booster. Instead of recreating that shape, I can repurpose already existing geometry. Again, you will notice that I'm not grabbing any features. I simply select existing design, select copy option, and using steering wheel, move it to a new location. Solid Edge is very flexible, as I mentioned earlier. It allows me to manipulate geometry in many different ways. I can change it using steering wheel, and in this case I'm gonna rotate it 180 degrees, and I'm pretty much done. We can also capture design intent using a relationship between faces. In this case I want to make sure that that flat face is tangent with the cylindrical face. Using face relate command, I will capture this relationship in persistent manner, and it will be saved with the part regardless of future changes. We can control geometry not only through relationship between faces, but we can capture design intent using dimensions, bypassing middleman sketch. I can apply dimension directly to 3D body and adjust the size as I want. Another way to actually get additional flexibility to your design is combine parametric features with synchronous method of design. So in this case I'm going to create this lofted protrusion in a fully parametric way. And for this you don't have to switch between different parts, it's all one single integrated environment. So as you can see I can quickly select faces and it will define the edges required. Not only that, I can also define the relationships, how this protrusion is related to adjacent geometry. In this case we want tangent. Now if I start changing my geometry in a synchronous way, you can see how geometry adjusts accordingly. It's a great way to add flexibility to your design. But in this case I'm going to open up my design. I'm going to just add additional 2 degrees to that angle, and you can notice regardless of the environment, whether it's ordered or synchronous, I can still manipulate my geometry with the steering wheel. Now I'm going to offset face and use that face to control the depth of my cutout. I need to add cutout to make this part a little bit lighter It's a racing bike after all. You can notice how quickly and efficiently I can include the whole face instead of trying to select single edges. At the same time, I can add offset while doing that. It all happens in one single operation. And now I will define that offset face as the bottom of my cutout. So let's get back into assembly and let's see how we're doing with our design to make sure the fit is where we need it to be. You can see that part is kind of dull, plus the shape is not what we want. But quite easily, without getting back into the part, we can start modifying geometry right here on the fly. I can select geometry, and using the same consistent method of manipulation, using steering wheel, I can adjust my shape drastically. And combination of synchronous and parametric features allows me to do this very easily. At the same time, I can rotate my design, and you can see how part will update without any problems. You can say I'm almost sculpting my part. The same way goes with the opposite end. Maybe we want to add additional angle at that end. Great flexibility there. But what if I need to modify my geometry and get rid of some features, or maybe add additional features? No problem, we can do this again on assembler level. I can select geometry from the part and manipulate it the same way as I'm doing it inside of the part environment. So let's say we want to get rid of this internal cutout, the cylindrical face. No problem. We can also relocate this cylindrical shape and use the reference points. I don't even have to know the distance. I just use steering wheel to pick the reference point, and it will perfectly align with that back face. What if we need to add additional protrusion? Not a problem. Right at assembly level, I can define the length, and add additional geometry. Let's add some treatment features. In this case, I want to create cutout. And again, I'm doing this at the assembly level, but cutout will be created in the part. How's this for productivity? While I'm doing this, I can also take advantage of offset. So that allows me to pick the side, which side I want to cut. And we're pretty much done. Created that cutout. How about treatment features? Again, the same way we can create them at assembly level. We're going to start with the chamfer and apply that chamfer to the outside edge. And all these features again are going to be placed inside of the part. Now let's add couple rounds. And finally we're going to create round for the majority of edges in that part. Just simply fence select the edges we need to round, and solid edge will do the rest. Again, all these features are going to be created inside of the part. So now that we're almost done with the part, we want to make sure that it meets our strength requirement. But before we do that, keep in mind this is a racing bike, so it needs to be as light as possible. So we need to move in that direction. Let's move the front face a little bit toward the back face to make it thinner. At the same time, we want to increase thickness on the other end of the lever. Using solid edge simulation inside of solid edge will allow us to evaluate the part and see if it meets the strength requirements. So let's go inside of the part, and before we analyze the part, I want to make sure that we simplify it, because all these extra small features are irrelevant for analysis. Solid edge simulation allows us to analyze the part in simplified state, and for that we're going to use some tools that will, for the purpose of the analysis, get rid of some small features. Now we can set up study and analyze the part. Solid edge simulation is one single integrated environment with solid edge, so we can quickly set up study, and we don't even have to select the part since we're doing analysis of a single part. Material is already transferred into study, and all we have to do is define loads and boundary conditions. So we're going to start with the loads. One thing I'd like to point out that when we define load, we use the same tool to manipulate the direction of the force as we use for manipulating geometry. Speaking of consistency, we're going to analyze against that cylindrical opening. So we're going to set up fixed constraint. And we're ready to mesh and solve. In one single click, we'll be able to mesh the part, bring all the information into an X-Nestron, and bring results back into post-processing window. An X-Nestron is an industry-proven solver which brings accurate results back into post-processing window. This environment is very flexible. It allows users to see stress, different stress concentrations. It allows users to see displacement. But in this case, after we animated the part and see how it performs under stress, we are interested in a factor of safety. In this case, we can set up factor of safety even to custom values. So in this case, we're interested from 1 to 2. And as you can see, we still have problem in that area. Because it's a one single integrated environment, we don't have to step out of this tool. We can just use the same steering wheel we used to design the part. We can use the same tool to modify it. So we need to make it thicker. So maybe that wasn't such a good idea to make it thinner on the front end. So we want to beef up the front end as well as the rear end of this lever. We still have room to add additional thickness there. And also we might want to shorten the whole design. Using the same steering wheel, we can just select the area that we want to modify and just shorten the part. We're not dealing again with any features. We're not looking for ways the part was designed, even if it was designed by somebody else. We can just select the area we need to modify and shorten the lever. We can right click on the study and say solve again. All the boundary conditions, all the meshing options, all of this information gets preserved, and now we get results back in post-processing window. We can go back to factor of safety and define it again, 1 to 2. And you can see that now we are green throughout the part, which means we met our strength requirements. Now we're back into assembly environment, and one last thing I would like to talk about is how easy it is in Solid Edge to set up assembly relationships. When we design that part, we design it at a certain location, but we didn't set up any relationships. Solid Edge provides assembly relationship assistant where we can define what parts we're looking to create relationships for, and system will do the rest. Quite easy, user-friendly. And once we've done that, we can go through all the relationships, pick the ones we want, and accept them. So now, once we define those relationships, we can easily make modification to any of the components and see the relationship, make the part stay in place, and move together with modified geometry. So let's go back to PowerPoint. Let's summarize the techniques that we have covered while working in Solid Edge. Solid Edge allows for reuse of existing geometry from neighboring components, accelerating design right from the start. Easily move a sketch to a new location and reuse for developing same 3D geometry again. Move or copy solid geometry to any new location to accelerate your design. Efficiently manipulate the geometry using steering wheel for rapid design changes. It works the same way on imported geometry, providing unmatched capabilities for working with suppliers or customers' data from a different CAD package. Intuitively constrain 3D geometry using face relationships even on imported unparameterized bodies. Capture design intent on the fly using dimensions and bypassing the middleman Sketch. Take advantage of one single integrated environment, combining direct model interaction with fully parametric features for greater flexibility. Change geometry at the assembly level for faster edits. Multiple components can be edited at once without the need to modify them one by one. Validate your design early in the design cycle using solid edge simulation and avoid costly mistakes down the line. And finally, automatically capture assembly relationships to eliminate tedious work of applying them manually to every component. The solid edge portfolio is focused on driving digital transformation for small and medium-sized companies. We see that these companies want complete, fully featured, and professional engineering tools. But they also need tools that are easy to access and easy to learn. As you saw in this webinar series, the solid edge portfolio is more than just solid edge CAD. It's a complete portfolio of solutions for design, simulation, manufacturing, and technical publications. Also, we have tools for collaboration and data management. Combined, these solutions speed the complete product development process. You can download a trial version of solid edge at the link shown here, or you can contact a local channel partner to learn more. If you would like to find out more about solid edge, again, you can call this number to speak to us directly. Or you can go to this link and download a trial version of solid edge that you can use for free for 45 days. Thank you for joining this webinar today. Enjoy the rest of your day.